Okay, so trig proofs are often a concept that people find to be a little bit challenging. Every year when we go do the test on this, about half the students do really, really well, and some people just get really torn up by it and they just don't know what to do. So I was going to throw out a couple of problems and just talk you through a few strategies. If you hear noises in the background, I've got a few students in here waiting for school to start. So anyway, so let's just go and get started right with what I have laid out for you. So the first thing is when you deal with trig proofs, I have kind of a series of rules that we have to deal with. One of them is that when you look at a trig proof, you can only modify one side. So when you look at the problem, you always want to decide which one looks more obnoxious. You know, which one looks like there's more work to be done. Second thing, you can only do one operation at a time, and that operation could be like a substitution, like take a tangent out and put a sine over a cosine, maybe take out a secant and call it 1 over cosine. There's a variety of those substitutions that we can make. I have a list of them over here. So notice that if I had a cosine squared, I could maybe replace it with a 1 minus sine squared. Maybe we could take a 1 plus tangent squared and replace it with a secant squared. There's all these various things that we could use from our identities. And then the last thing is make sure that your answer is reflexive, which means your final answer needs to be something like sine x equals sine x. They have to be identical. Now, I have a series of strategies that I use as I do these problems. One of them is if that a problem looks kind of complicated and I don't know what to do, the first thing I do is like, well, I guess I can turn everything into sines and cosines because everything, secants, cosecants, tangents, they're just all versions of sines and cosines. So that's the first strategy that I have set up right here. So when I look at tangent plus secant equals this, and I want to prove this, I will start by changing this tangent to a sine over cosine. And of course, a secant is 1 over the cosine. And notice I'm not going to touch this side over here because we said we're only going to modify one side at a time. Now, my second strategy is looking for common denominators, but you'll notice in this particular problem, I got that already. Now, so since I have a common denominator, what I'm going to do is I'm going to put these together. And I know that I'm going to change the order of this. And it's because I've done problems like this a few times, and I've noticed that something is actually kind of nicer in this way. Now, so that's my first strategy, is looking for sines and cosines. My second is making sure you have common denominators if you have multiple fractions. The next one is this idea of conjugates, and that's something that you used back in Algebra 2. If you had 1 plus 2i, we used to multiply by 1 minus 2i. We had that for our conjugate roots theorem in here as well. So it turns out for me, what I like to do sometimes is I like to multiply something like a 1 plus by a 1 minus sign. That's what I call my conjugate trick. Now, this is just kind of a trick, and it's because it's something that I've noticed works well. But it lines up with what I put number 4. I said push towards what you need. And if you look over here, what I need is a 1 minus sign in the bottom. And you'll notice that I kind of made that happen. By using this conjugate, it pushed me towards that value. So if I were to distribute the top, I would get 1 minus the sine squared all over 1 minus sine cosine. Now, keep in mind, this is what I'm shooting for, and I'm hoping I'm going to get there. I don't think I gave myself enough room on this paper, but we're getting there close. Because I can see right here that 1 minus sine squared by the Pythagorean identity, 1 take away sine squared, would be cosine squared. So if I replace this 1 minus sine squared right here with cosine squared, I have 1 minus sine cosine, and that's another little strategy I didn't bother to write down, is that I did not distribute the bottom because I was hoping towards keeping this intact. So I'm almost out of space, but if I cancel those two cosines, you'll notice that I have 1 cosine on top and a 1 minus the sine at the bottom, which is exactly what I wanted to see over here. Notice that is what I was trying to get. My answer is reflexive. And so that means I have demonstrated beyond any doubt that that is actually a true statement, that this value is the same as this one. So The second one, again, actually, interestingly enough, as I picked it out, I was trying to highlight this conjugate idea. Now, some people look at one side, some people look at the other side. In this particular example, I'm going to go ahead and look at the left side, although it doesn't have to always be the left side. Just the examples that I picked are going that way. So I want to highlight that conjugate trick that I told you a moment ago. I'm going to multiply the top and the bottom by 1 plus sign. Now again, hinting over here, notice that also pushes me towards what I want because I wanted a 1 plus sign on top and I just made it happen. But because I want that 1 plus sign, I hope it stays around in the long run because I'm hoping this cosine is going to cancel because I want that thing. And I've got 1 minus sine squared. Notice yet again, we have this little Pythagorean identity. Anytime you have a square, you want to think about those Pythagorean identities. So I've got my sine of beta, 1 plus sine cosine, and 1 minus sine squared. We just saw that in that previous problem, that 1 minus the sine squared is in fact cosine squared. And so this is again cosine squared beta. And so if we could cancel those out, we end up with, those cancel and I get with a 1 plus sine beta on top. Sometimes it's hard to write sine beta for me. And cosine beta, that's just not the language we normally speak. And so I've got my answer, and you'll notice again, it was reflexive. I got what I was shooting for. Okay, so that's 2 examples. So notice that as I go through this, I'm looking for that. Now, the last problem that I was going to show you is this one right here, which is actually technically one of the more complicated problems, but there's something there that's kind of awesome. I want a cosecant. So notice that I'm going to go ahead and modify this because it looks harder, but I want a cosecant, which means I want a sign in the bottom. So now notice, if I want a sign in the bottom, if you look at this piece right here, what I hope you can catch is it already has kind of the structure that I want, which for me tells me I might get away with not doing anything to it. I'm just going to let it hang out. So my first thing is don't even touch this piece, although I can do it a different way that'll show you that it will work. So I'm going to go ahead and use the conjugate trick that we have used on those other problems by using a 1 minus cosine, top and bottom of this question. And so I've got 1 minus cosine times the sine. And when we distribute it, we get 1 minus cosine squared. Now, that's not the same as what we had in the previous problems, but it's awfully close. Because you'll notice I got 1 minus cosine sine. Haven't done anything. But as we see, that 1 minus the cosine squared, 1 take away the cosine squared is in fact sine squared. Now keep in mind, peeking over here, I'm not touching it, but I want sines in the bottom, and I just got closer. And things are going to get better because those would cancel, and I get 1 minus the cosine over the sine. Now, recalling the steps that we talked about, we'd like to get sines and cosines. We have that. I'd like a common denominator. Notice we have that as well. So I guess if we have a common denominator, we can add them together. So I'm going to go ahead, and this should be below it, but I don't have any more room. So when I add my numerators, notice the cosines cancel, and I've got 2 over the sine. And then 2 divided by the sine is 2 cosecants. There we go. And that's exactly what we wanted. And as we mentioned in class, when we're all done with those problems, we put a little box down there saying that we're confident that we finished. Now, just for the sake of showing you another way, because sometimes you might not think to do the problem the way that I did. You might have tried something else. So I will show you one more version of that problem. Because I did want you to see that sometimes you try one thing and it works. Sometimes you try something else and it works also. So it's not like there's only one way to do these problems. So one of the strategies that I mentioned is we like to go ahead and use common denominators. So a lot of students will look at this thing right here What do you need, son? Okay. Anyway, some people would say, well, I'm going to go ahead and make a common denominator. So now I said do one thing at a time, but really you might say, aren't you doing two things right here by multiplying both by the other denominators, 1 plus cosine over here and sine over here? I kind of consider that being one thing, because really all I'm doing is making common denominators. I'm not multiplying and simplifying and reducing. I'm just doing a simple concept. So what I have now is sine squared t over sine t 1 plus cosine t. And then over here, this is a little bit tricky, but this has to be fully distributed. So if I multiply this, 1 times 1 is 1. I get 2 cosines of t plus cosine squared t. Now, a lot of people would get to this part of this problem and feel a little bit scared off, like I've made a mistake, and this is getting a little bit complicated. It's looking a little bit large. But as it turns out, because we have a common denominator, there's something that is kind of nice that's going to happen. So let's see what we got. I've got a sine squared t plus 1 plus 2 cosine t plus cosine squared t. Now, again, looking kind of bad. However, you might see, if you're looking carefully, that right here you've got a sine squared plus a cosine squared, which we know that sine squared plus cosine squared is explicitly the number 1. Oh, well, that got a little bit nicer. So I got 1 plus 1 plus 2 cosine t all over that stuff that we had in the denominator. And then clearly we have 1 plus 1 is 2. This is the part where trig proofs, they are formal. So sometimes you're like, dang, it's a lot of steps, but none of the steps are necessarily that hard. And then I noticed these both have a 2 in common. So if I factored out the 2, I'm to this place. And I hope you can see something kind of cool happening, because those would cancel. And I'm down to 2 over the sine, which, what do you know, is 2 cosecants of t. Woo! This entire problem is right. Now that looks like I did a whole lot of work, but it's just a lot of work because I had to show line by line the steps. I think that makes it hard for people, because sometimes they can see the solution a little bit faster, but you got to slow yourself down a little bit. So that's kind of a lengthy version. Notice this other version was just a little bit faster, but just because you picked a version that may seem a little bit harder doesn't mean it's not valid. And so sometimes, hey, getting it done is what we're after. So hopefully that was helpful to you, and I'll see you back in class. Bye.